Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The solar wind that flows through space. From the surface of the sun, an invisible river flows outward in all directions, streaming past the planets and extending far beyond the orbit of Pluto into the distant reaches of the solar system. This is the solar wind, a continuous flow of charged particles, primarily electrons and protons, that escape from the sun's outer atmosphere and race through space at speeds ranging from 250 to over 500 miles per second. This wind carries with it pieces of the sun itself, along with magnetic fields that thread through the solar system, creating an enormous bubble of solar influence that shapes the space environment around every planet. The story of the solar wind begins in the sun's corona, the outermost layer of the solar atmosphere that extends millions of miles above the visible surface. The corona is paradoxically much hotter than the surface below it, while the sun's visible surface, the photosphere, has a temperature of about 10,000 degrees Fahrenheit. The corona reaches temperatures exceeding 2 million degrees. This extreme heating, still not completely understood, but likely involving magnetic fields and wave energy, gives particles in the corona so much energy that many of them move faster than the sun's escape velocity. Imagine standing at the sun's surface and throwing a baseball upward. To escape the sun's gravity, you would need to throw it at about 380 miles per second. In the corona, thermal energy heats particles to such extreme temperatures that a significant fraction of them are moving faster than this escape velocity. These particles don't fall back to the sun. They stream away into space, carrying energy and momentum with them. The sun is essentially evaporating, losing mass continuously through this process, though at a rate so slow that it would take trillions of years to evaporate completely. The solar wind is not uniform. It flows faster from some regions of the sun than others, creating a complex structure as it expands outward. Above the sun's equatorial regions, where magnetic field lines tend to loop back to the surface, the solar wind emerges more slowly, typically around 250 miles per second. But at the sun's poles and in coronal holes, regions where magnetic field lines extend far into space, rather than looping back, the wind flows much faster, reaching speeds of 500 miles per second or more. These variations in speed create interaction regions where fast solar wind catches up to slow solar wind. Imagine cars on a highway where fast-moving traffic overtakes slower-moving traffic. The fast solar wind compresses the slow solar wind ahead of it, creating regions of enhanced density and magnetic field strength. These co-rotating interaction regions, named because they rotate with the sun as it spins, sweep through the solar system like a spiral pattern, buffeting planets with alternating streams of slow and fast wind. As the solar wind flows outward, it carries the sun's magnetic field with it. The magnetic field lines become stretched and twisted, creating a spiral pattern much like water from a rotating garden sprinkler. This interplanetary magnetic field threads through the entire solar system, connecting magnetically active regions on the sun to the distant reaches of space. When magnetic field lines from different regions of the sun come together, in space they can reconnect, releasing energy and accelerating particles to even higher speeds. The solar wind is not just a steady breeze but includes violent gusts and storms. When an eruption occurs on the sun, a solar flare or a coronal mass ejection, enormous quantities of plasma and magnetic field can be hurled into space far faster than the normal solar wind. A coronal mass ejection can contain billions of tons of material moving at speeds up to several thousand miles per second. When one of these structures reaches Earth, typically 1 to 3 days after leaving the Sun, it can compress Earth's magnetic field, trigger spectacular auroras, and potentially disrupt satellites, power grids, and communication systems. The journey of a solar wind particle from the Sun to Earth takes about 4 to 5 days travelling at typical speeds. During this journey, the particle encounters very little. Space between the Sun and Earth is remarkably empty. A cubic inch of the solar wind near Earth contains only about 5 to 10 protons, far more tenuous than even the best vacuum we can create in laboratories on Earth. Yet despite this extreme sparseness, the solar wind carries significant momentum and energy simply because of the vast volume through which it flows and the speeds at which it travels. When the solar wind encounters a planet, what happens depends on whether that planet has a magnetic field. Earth's magnetic field creates a protective bubble called the magnetosphere that deflects most of the solar wind around the planet. The interaction is dynamic and complex. The leading edge of Earth's magnetosphere, called the bow shock, is where the supersonic solar wind first encounters Earth's magnetic field and slows down abruptly, much like air piling up in front of a supersonic aircraft creates a shock wave. This shock heats the solar wind and diverts it around Earth's magnetosphere, creating a turbulent boundary layer called the magnetosheath. Some solar wind particles do manage to penetrate into Earth's magnetosphere, particularly when reconnection occurs between the interplanetary magnetic field and Earth's magnetic field. These particles get funneled along Earth's magnetic field lines toward the polar regions, where they collide with atoms in the upper atmosphere, creating the shimmering curtains of light we call auroras. The green and red colours come from oxygen atoms at different altitudes being excited by these collisions, while nitrogen produces blue and purple hues. Planets without magnetic fields like Mars and Venus experience the solar wind very differently. Without a protective magnetic bubble, the solar wind interacts directly with the upper atmosphere. Over millions of years, this interaction strips away atmospheric particles, carrying them off into space. Mars, which once had a thicker atmosphere and possibly liquid water on its surface, has lost much of its atmosphere to this process. The solar wind literally peels away the outer layers of the Martian atmosphere, particularly during strong solar storms, gradually transforming Mars from a potentially habitable world to the thin, dry atmosphere we observe today. The Moon, with neither atmosphere nor magnetic field, receives the full force of the solar wind directly on its surface. Solar wind particles impact the lunar regolith, becoming implanted in the soil. Over billions of years, this process has altered the chemistry and appearance of the lunar surface, darkening it and creating what scientists call space weathering. Ancient lunar rocks brought back by Apollo astronauts contain trapped solar wind particles that serve as a record of how the Sun's output has changed over time. Giant planets like Jupiter and Saturn have enormous magnetospheres that extend millions of miles into space. Jupiter's magnetosphere is so large that if we could see it from Earth, it would appear several times larger than the full moon in the sky. The solar wind compresses these magnetospheres on the side facing the Sun and stretches them into long tails on the night side. Within these giant magnetospheres, the interaction between the solar wind, the planet's magnetic field, and particles from the planet's moons creates some of the most intense radiation environments in the solar system. The solar wind doesn't flow forever. Far from the Sun, billions of miles beyond the orbits of the planets, it begins to slow down as it encounters the interstellar medium, the dilute gas and plasma that fills the space between stars. The Voyager spacecraft, launched in 1977, have travelled far enough to cross the boundary where the solar wind slows to subsonic speeds, called the termination shock. This boundary is not spherical, but is pushed outward in the direction the solar system is moving through the galaxy and compressed in the opposite direction. Beyond the termination shock lies a region called the heliosheath, where the solar wind has slowed but still moves outward, compressed and heated by its interaction with the interstellar medium. The exact shape and extent of this region depend on the strength of the solar wind and the pressure of the interstellar medium outside. Voyager 1 and Voyager 2 have now crossed even farther, passing through the heliopause, the outer boundary where the solar wind effectively stops and interstellar space begins. They are now in a region where the dominant flow is no longer from the Sun, but from the galaxy itself. The structure created by the solar wind, this vast bubble of solar influence, extending billions of miles in all directions, is called the heliosphere. It serves as a partial shield, deflecting some of the cosmic rays that stream through the galaxy. Without this protection, the flux of high-energy particles reaching the inner solar system would be higher, potentially affecting planetary atmospheres and creating more radiation hazards for any life on planetary surfaces. The solar wind varies with the Sun's activity cycle. During solar maximum, when the Sun is most active with many sunspots and frequent eruptions, the solar wind is stronger, more variable, and more likely to include fast-moving coronal mass ejections. During solar minimum, when the Sun is quieter, the wind becomes more regular, though still continuous. This 11-year cycle affects space weather throughout the solar system, influencing everything from auroral activity on Earth to the radiation environment encountered by spacecraft. The composition of the solar wind provides a sample of the Sun's outer layers. While predominantly hydrogen, both protons and electrons, the wind also contains helium, making up about 4% of the particles, along with trace amounts of heavier elements, like carbon, nitrogen, oxygen, neon, magnesium, silicon, and iron. These heavier elements are present in much smaller quantities but provide valuable information about solar composition and the processes occurring in the corona. Different types of solar wind have different characteristics. The slow solar wind is denser and cooler, while the fast wind is more tenuous but carries more kinetic energy due to its higher speed. Transient events like coronal mass ejections create temporary structures in the solar wind with dramatically enhanced density, speed, and magnetic field strength. These variations create a constantly changing space environment that spacecraft and planets must navigate. The solar wind also carries information outward from the Sun. Disturbances created by solar activity propagate through the solar wind, and by observing how these disturbances evolve and interact as they move through space, scientists can learn about the properties of the wind itself and the magnetic fields threading through it. Spacecraft throughout the solar system serve as sentinels, measuring the solar wind's properties at different locations and providing a three-dimensional view of how this invisible river flows through our cosmic neighborhood. Every star produces a stellar wind, analogous to our solar wind, and these winds play important roles in stellar evolution and in shaping the environments around other planetary systems. Hot, massive stars produce fierce stellar winds that can carry away significant fractions of the star's mass over its lifetime. Cool, evolved stars like red giants produce slower but denser winds. Understanding our own solar wind provides insights into these stellar winds throughout the galaxy, connecting the processes occurring in our immediate space environment to the broader evolution of stars and planetary systems across the universe. What alien oceans might contain? Earth's oceans are vast, salty bodies of liquid water covering more than 70% of the planet's surface, containing dissolved minerals, organic molecules, and a staggering diversity of life, from microscopic bacteria to the largest animals that have ever existed. But oceans on other worlds might be fundamentally different, not just in what organisms inhabit them, but in their very composition, what liquids fill them, what chemicals dissolve in those liquids, and what physical conditions prevail at their depths. Understanding what alien oceans might contain means considering not only water-based oceans with different chemistry than Earth's seas, but entirely different liquids that could serve as oceanic solvents on worlds with radically different temperatures, pressures, and geological histories. The most familiar alien oceans would be water-based oceans on other worlds. Several candidates exist in our own solar system. Europa, Jupiter's ice-covered moon, harbours a global ocean containing perhaps twice as much liquid water as all of Earth's oceans combined, kept liquid by tidal heating from Jupiter's gravity despite surface temperatures around -160 degrees Celsius. This ocean lies beneath an ice shell estimated to be 15 to 25 kilometers thick, shielding the water from the vacuum of space and from Jupiter's intense radiation belts. What Europa's ocean contains remains unknown, but scientific models and the limited data from spacecraft flybys provide clues. The ocean is certainly salty, likely containing dissolved salts leached from Europa's rocky seafloor over billions of years. Magnesium sulfate, sodium chloride, and other salts detected spectroscopically in Europa's ice shell probably came from the ocean below. The salinity might be similar to Earth's oceans, or it might be substantially higher, creating a briny sea where salt concentrations affect water's freezing point, density, and chemistry. High salinity would influence what kinds of life could potentially evolve, favouring organisms with mechanisms to cope with osmotic stress. The ocean would be dark. Absolutely no sunlight penetrates through kilometres of ice. Any life in Europa's ocean would depend on chemical energy rather than photosynthesis. The rocky seafloor might host hydrothermal vents similar to those on Earth's ocean floor, where hot, mineral-rich water spews from cracks in the rock, driven by volcanic heat from the moon's interior. These vents could provide energy and nutrients to support chemosynthetic bacteria that extract energy from chemicals in the vent fluids: hydrogen, methane, hydrogen sulfide, iron compounds. If such microbes exist, they might form the base of a food chain, supporting more complex organisms analogous to the tube worms, clams, and crustaceans that cluster around Earth's hydrothermal vents. Dissolved gases would be present in Europa's ocean: carbon dioxide from reactions between water and rock, hydrogen from water-rock reactions, and possibly from radiolysis, where radiation breaks apart water molecules near the ice-ocean boundary, methane from geological processes, or potentially from biological activity. The concentrations and ratios of these gases would reveal much about the ocean's chemistry and whether biological processes might be occurring. Organic molecules, carbon-based compounds, almost certainly exist in Europa's ocean. Comets and meteorites containing organic compounds have bombarded Europa throughout its history. Chemical reactions between water and rock produce simple organic molecules. If life exists, it would produce far more complex organic molecules: amino acids, lipids, sugars, proteins. Detecting complex organic molecules in samples from Europa's ocean would be strong evidence for biology, though distinguishing biological from non-biological organic chemistry would require careful analysis. Enceladus, Saturn's small moon, provides an even more accessible alien ocean because it actively vents ocean water into space through cracks in its south polar ice shell. The Cassini spacecraft flew through these plumes, analysing their composition directly. The plumes contain water vapour, ice grains, carbon dioxide, methane, ammonia, molecular hydrogen, and complex organic molecules, including some with chains of carbon atoms, ingredients that on Earth would suggest habitability. The presence of molecular hydrogen is particularly intriguing because it suggests water rock reactions at high temperatures, consistent with hydrothermal vents on Enceladus's seafloor. The organic molecules, while not proof of life, show that organic chemistry is occurring in Enceladus's ocean. Titan, Saturn's largest moon, presents an entirely different type of ocean, not water, but liquid hydrocarbons. Titan's surface temperature hovers around -180 degrees Celsius, far too cold for liquid water, which is frozen as hard as rock. But at these temperatures, methane and ethane exist as liquids. Titan has lakes and seas of liquid hydrocarbons near its poles, bodies of liquid methane and ethane with dissolved propane, butane, nitrogen, and traces of more complex organic molecules. These hydrocarbon seas are hundreds of meters deep in some places, creating environments completely unlike anything on Earth. What Titan's hydrocarbon oceans might contain depends on what chemistry can occur in liquid methane at cryogenic temperatures. Organic chemistry certainly happens. Titan's atmosphere produces complex organic molecules through photochemistry, and these molecules rain down onto the surface, accumulating in the lakes and seas. Nitrogen compounds, cyclic molecules, long-chain hydrocarbons, and possibly even more complex molecules might dissolve in the methane. Whether life could exist in liquid methane remains highly speculative, but if it does, it would use completely different biochemistry than Earth life, perhaps with cell membranes made from molecules that are insoluble in hydrocarbons rather than the water-soluble membranes Earth organisms use. Titan also likely has a subsurface water ocean beneath its icy crust, similar to Europa and Enceladus. This buried ocean would be separate from the surface hydrocarbon seas, creating the possibility that Titan might host two completely different types of chemistry: water-based chemistry in the deep subsurface ocean and hydrocarbon-based chemistry in the surface seas. Whether these two environments could both support life, and whether life in one could be related to life in the other, represents one of the most intriguing questions about this remarkable moon. Ammonia oceans represent another possibility for alien seas. Ammonia remains liquid at temperatures between -77 and -33 degrees Celsius at Earth atmospheric pressure, colder than water but warmer than methane. A planet or moon with temperatures in this range might have oceans of liquid ammonia or ammonia-water mixtures. Pure ammonia is a less effective solvent than water for many compounds, but it can dissolve different substances than water, creating entirely different ocean chemistry. An ammonia ocean would be less dense than water ice, so ammonia ice would sink rather than float, potentially affecting planetary heat transport and ocean circulation. The ocean's pH would be highly alkaline. Ammonia is a base, creating chemistry very different from Earth's near-neutral oceans. Organisms adapted to ammonia oceans would need biochemistry that functions at low temperatures and high pH, potentially using ammonia molecules in ways analogous to how Earth life uses water. Sulfuric acid oceans sound implausible, yet Venus's clouds contain concentrated sulfuric acid droplets, and some scientists have speculated about life existing in these droplets. While Venus's surface is hellishly hot, the cloud layers at altitudes of 50 to 60 kilometers above the surface have temperatures around room temperature, quite comfortable by terrestrial standards. If life could exist as airborne organisms living in cloud droplets, those droplets would be concentrated sulfuric acid, requiring biochemistry completely unlike anything on Earth. Certain Earth microbes can tolerate extremely acidic conditions, proving that acid-resistant biochemistry is possible. But whether life could actually live in sulfuric acid remains unknown and highly controversial. Silicate oceans, molten rock, might exist on lava worlds orbiting extremely close to their stars. At temperatures exceeding 2000 degrees Celsius, rock melts into liquid magma that flows like water. While most scientists consider molten rock too hot and destructive for any conceivable biochemistry, some speculative theories propose exotic life forms based on completely different chemistry that might exist in magma, perhaps using silicate molecules or metal compounds as structural materials instead of carbon-based organic molecules. Such life would be so alien that we might not recognize it as life, even if we observed it directly. Supercritical oceans exist under conditions where temperature and pressure are high enough that the distinction between liquid and gas breaks down. Supercritical water, existing at temperatures above 374 degrees Celsius and pressures above 220 atmospheres, has properties intermediate between liquid and gas. Deep beneath the surfaces of massive ocean worlds, pressures might be high enough to create supercritical water oceans. The chemistry in supercritical water differs dramatically from normal water chemistry, with different solubilities, reaction rates, and molecular interactions. Whether life could adapt to supercritical conditions remains unknown, but the possibility can't be ruled out for extremely exotic organisms. The ocean floor composition profoundly affects ocean chemistry. Earth's ocean floors are basaltic rock, and water-rock interactions continuously cycle elements between the ocean and the crust. Alien ocean floors might be different, perhaps pure ice if the ocean is deep enough that high-pressure ice forms at the bottom, or perhaps carbonate rocks, serpentinite, or other minerals depending on the planet's composition. These different minerals would leach different elements into the ocean, creating different dissolved chemistry. Hydrothermal vents on alien seafloors might vent fluids with very different composition than Earth's vents. On Europa or Enceladus, where the rocky interiors might be rich in different minerals than Earth's mantle, vent fluids might contain unusual concentrations of metals, sulfur compounds, or other chemicals. These different chemistries would favor different types of chemosynthetic organisms if life exists, potentially creating ecosystems with no analogue on Earth. Dissolved oxygen would be rare or absent in most alien oceans unless photosynthetic life has evolved and produced oxygen for billions of years as on Earth. Most alien oceans would be anoxic, without dissolved oxygen, more similar to Earth's oceans before the Great Oxidation Event 2.5 billion years ago. Anoxic oceans contain different dissolved metals and have different chemistry than oxygenated oceans. Iron remains dissolved in anoxic water instead of precipitating as rust. Sulfur chemistry dominates, rather than oxygen chemistry. Life in anoxic alien oceans would use anaerobic metabolism, extracting energy from reactions that don't involve oxygen. Temperature gradients in alien oceans depend on heat sources. Earth's oceans are heated from above by sunlight and from below by geothermal heat, creating complex circulation patterns. Europa's ocean, heated only from below by tidal heating and with a cold ice ceiling above, might have upside-down circulation compared to Earth. Warm water rising from the seafloor toward the ice ceiling where it cools and sinks back down. These circulation patterns would affect nutrient distribution, temperature zones, and where life might be most abundant. Pressure increases with depth in any ocean, but the rate depends on the liquid's density and the world's gravity. Europa's ocean might reach pressures exceeding 10,000 atmospheres at the seafloor, much higher than Earth's deepest ocean trenches, due to the ocean's great depth. Organisms adapted to such extreme pressure would have specialized biochemistry that functions under conditions where molecules are compressed and reaction rates are altered by pressure's effects on molecular structure. Seasonal variations might affect some alien oceans. A planet with significant axial tilt would experience seasonal changes in star heating that could affect surface ocean temperatures, causing seasonal mixing, ice formation and melting, and biological cycles tied to seasons. Tidally locked planets would have no seasonal variations, but might have temperature zones related to distance from the substellar point, the location where the star is directly overhead, creating warm equatorial regions and cold polar regions with different ocean chemistry in each zone. Ice-covered oceans might have ecosystems concentrated near the ice-water boundary, where any photosynthesis using radiation penetrating through cracks in the ice could occur, or where chemical gradients between the ice and deep ocean create energy harvesting opportunities. Life might cluster in cracks and crevices in the ice ceiling, or in regions where the ice is thinnest and most likely to crack or melt. What alien oceans might contain ranges from the familiar, salty water with dissolved minerals and potentially abundant life, to the exotic, liquid methane seas with dissolved organic compounds, ammonia oceans at cryogenic temperatures, supercritical fluids blurring the line between liquid and gas, even molten silicate magmas on scorching hot worlds. Each ocean's composition reflects its world's temperature, pressure, geology, and history, creating environments where chemistry operates under different rules, where life, if it exists, would be adapted to conditions we can barely imagine, where exploration by future spacecraft might reveal ecosystems as diverse and wondrous as Earth's oceans, or so alien that we struggle to recognize biology when we see it, expanding the inventory of habitable environments to include not just Earth-like water oceans, but any stable liquid where dissolved chemicals, energy sources, and sufficient time might allow chemistry to evolve into biology beneath the waves of alien seas scattered across the solar system and beyond. What is dark matter, and why can't we see it? Imagine trying to understand a conversation in a crowded room while wearing earplugs. You can see people's mouths moving, see their gestures, watch them react to each other, but you can't hear the words being spoken. You know communication is happening, the evidence is clear in the movements and responses, but the medium of that communication remains completely inaccessible to you. This is somewhat like humanity's relationship with dark matter. We can see its effects throughout the universe, observe how it shapes galaxies and bends light, measure its gravitational influence on everything around it. Yet the substance itself remains invisible and intangible to every instrument we've built to observe the cosmos. Dark matter makes up approximately 85% of all matter in the universe. Let that sink in for a moment. Everything you can see, every star, every galaxy, every glowing nebula, every planet, every atom in your body represents only about 15% of the matter that exists. The rest, the overwhelming majority, is dark matter, and it surrounds us, permeates us, flows through us, yet reveals itself only through its gravitational effects. The story of dark matter's discovery begins not with a sudden revelation, but with decades of observations that didn't quite make sense. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a collection of over 1,000 galaxies bound together by gravity. He measured how fast these galaxies were moving within the cluster and used these velocities to calculate how much mass must be present to keep the cluster gravitationally bound. What he found was shocking. The galaxies were moving so fast that they should have escaped the cluster's gravity and flown apart long ago, unless the cluster contained far more mass than could be seen in the form of stars and gas. Zwicky proposed that some form of dark matter must exist, matter that didn't emit light, but provided the additional gravity needed to hold the cluster together. His idea was largely ignored for decades. It seemed too radical, too strange. Surely there was a simpler explanation. Perhaps astronomers were just missing some normal matter, dust clouds or dim stars that hadn't been detected yet. But the evidence kept accumulating. In the 1970s, astronomer Vera Rubin conducted detailed studies of how stars and gas move within spiral galaxies. According to the laws of gravity and orbital mechanics, objects farther from the center of a galaxy should move more slowly, just as planets farther from the Sun orbit more slowly than those closer in. Mercury races around the Sun in just 88 days, while distant Neptune takes 165 years to complete one orbit. The same principle should apply to galaxies. Stars near the edge should crawl along in their orbits compared to stars closer to the galactic center. But that's not what Rubin found. She observed that stars at the outer edges of galaxies moved just as fast as stars closer to the centre, sometimes even faster. The rotation curves of galaxies were flat rather than declining, which could only mean one thing: there was far more mass in these galaxies than could be accounted for by visible stars and gas. And this extra mass wasn't concentrated at the centre where most of the visible matter was. It extended far beyond the visible disk, forming a massive spherical halo of invisible matter surrounding each galaxy. Picture a galaxy in your mind, a spiral with graceful arms of stars spinning around a bright central bulge. Now imagine that entire visible structure is embedded within a much larger sphere of dark matter, extending perhaps 10 times farther than the visible stars reach. This dark matter halo contains several times more mass than all the stars, gas and dust combined, yet it emits no light, no radio waves, no X-rays, nothing we can detect directly. The evidence for dark matter extends far beyond galaxy rotation curves. Gravitational lensing provides some of the most compelling proof. According to Einstein's theory of general relativity, mass warps the fabric of spacetime, and light follows the curves in this warped spacetime. When light from a distant galaxy passes near a massive object, its path bends. Just as light bends when passing through a glass lens. The amount of bending depends on how much mass is present. Astronomers observe light from distant galaxies being bent and distorted as it passes through galaxy clusters. By measuring this distortion carefully, they can map out exactly where mass is concentrated in these clusters, creating what's essentially a gravity map. When they do this, they find that most of the mass, about 90%, isn't where the visible galaxies are. It's distributed in a much larger structure, consistent with massive halos of dark matter. One of the most dramatic examples came from studying a structure called the Bullet Cluster, where two galaxy clusters had collided and passed through each other. During the collision, the hot gas from each cluster, which is normal matter, slowed down and remained near the collision site, heated by the impact. But the dark matter from each cluster, which doesn't interact with normal matter except through gravity, passed right through and continued moving. By mapping the gravity through gravitational lensing, astronomers could see that most of the mass had separated from the visible gas, providing direct evidence that dark matter and normal matter are distinct substances. So what is dark matter made of? This is one of the deepest mysteries in physics. And the honest answer is that we don't know. We know what it isn't. It's not made of atoms, protons, neutrons, or electrons. It's not any form of normal matter that we're familiar with. We call normal matter baryonic matter, and dark matter is something entirely different, something that exists outside the catalogue of particles that make up everything we can touch and see. The most popular hypothesis is that dark matter consists of particles that simply don't interact with electromagnetic radiation. Light, radio waves, X-rays, any form of light across the entire spectrum. These hypothetical particles, often called WIMPs, weakly interacting massive particles, would have mass and exert gravity, but they wouldn't emit, absorb, or reflect light. They would be essentially transparent to electromagnetic radiation, which is why we can't see them. Imagine a particle that could pass through matter almost as if it weren't there. Billions of these particles might be flowing through your body right now, passing through the Earth, streaming through space, and you would never know. They don't collide with atoms, don't scatter off electrons, don't leave any trace except for their collective gravitational influence. This is what dark matter particles would be like. Ghost particles that fill the universe, but interact with normal matter only through the weakest of forces. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and background radiation, trying to catch the rare interaction of a dark matter particle with normal matter. These detectors contain tanks of specially purified materials, cooled to near absolute zero, instrumented with sensors that can detect the tiniest energy deposit. The idea is that occasionally, very rarely, a dark matter particle might collide with a nucleus in the detector, releasing a tiny amount of energy that could be measured. So far, despite decades of searching with increasingly sensitive experiments, no one has definitively detected a dark matter particle. Another possibility is that dark matter consists of primordial black holes that formed in the early universe, not from collapsing stars, but from density fluctuations shortly after the Big Bang. These would be dark by their very nature, since black holes don't emit light. However, careful observations suggest that primordial black holes can't account for all the dark matter. They would produce observable effects, like gravitational microlensing when they pass in front of distant stars. And we don't see these effects at the level that would be expected if most dark matter were in this form. Some theories propose that dark matter might be axions, extremely light particles that were produced in enormous quantities in the early universe. These would be very different from WIMPs, much lighter, much more numerous, behaving more like a wave than individual particles. Detecting axions requires different experimental approaches, and several experiments are currently searching for these elusive particles. There's even a possibility, though most physicists consider it less likely, that dark matter doesn't exist at all. Instead, perhaps our understanding of gravity is incomplete, and the theory needs to be modified to explain the observations without requiring invisible matter. These modified gravity theories, called MOND, modified Newtonian dynamics, and various relativistic extensions, can explain some observations but struggle with others, like the bullet cluster, which seems to require actual dark matter to explain. Dark matter played a crucial role in the formation of structure in the universe. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny variations in density. These variations were the seeds of all future structure: galaxies, galaxy clusters, and the cosmic web. But normal matter coupled to radiation in the early universe couldn't collapse and clump together efficiently. Dark matter, which didn't interact with radiation, could begin collapsing earlier, forming gravitational wells that normal matter eventually fell into. Without dark matter, galaxies as we know them couldn't have formed in the time available since the Big Bang. Today, dark matter continues to shape the universe. It forms the gravitational scaffolding along which galaxies are distributed. It determines how galaxy clusters form and evolve. It affects how galaxies merge and interact. Every large-scale structure in the universe exists because of dark matter's gravitational influence. On smaller scales, dark matter fills our own galaxy. The Milky Way sits within a dark matter halo that extends far beyond the visible disk of stars. This halo contains perhaps 10 times more mass than all the stars in the galaxy. As our solar system orbits the galactic center, we're moving through this sea of dark matter. At any given moment, thousands of dark matter particles might be passing through every cubic centimeter of space, though detecting even one of them remains beyond our current capabilities. The invisibility of dark matter is not a limitation of our instruments. It's a fundamental property of the substance itself. We can't see it because it doesn't interact with light in any way. We can't build a better telescope or a more sensitive camera to observe it directly. The only way we know it exists is through its gravitational effects on the things we can see. It reveals itself in the motion of stars, the bending of light, the structure of the cosmic web, and the evolution of the universe itself. Dark matter surrounds us, shapes the cosmos, and yet remains one of the deepest mysteries in science, a reminder that the universe is far stranger and more complex than our everyday experience might suggest. Why alien life might not use DNA deoxyribonucleic acid, is the molecule of heredity for nearly all life on Earth. From bacteria to blue whales, from mushrooms to sequoia trees, every organism uses DNA to store genetic information, to pass traits from parents to offspring, and to direct the construction of proteins that build and maintain living cells. DNA's structure is elegant and famous, a double helix of two strands twisting around each other, each strand composed of a sugar-phosphate backbone with 4 types of bases attached in sequences that encode genetic instructions. DNA seems so fundamental to life that it's easy to assume it must be universal, that any living thing anywhere in the universe would use DNA. But this assumption is almost certainly wrong. DNA is not the only molecule capable of storing and transmitting genetic information, and the specific chemistry that makes DNA work on Earth might not be optimal or even possible under different planetary conditions. To understand why alien life might not use DNA, we first need to understand what DNA actually does and what properties make it suitable for its role. DNA serves 3 critical functions. First, it stores information. The sequence of bases along the DNA strand encodes instructions for building proteins and regulating cellular processes. Second, it replicates. DNA can be copied with reasonable accuracy, allowing genetic information to be passed from one generation to the next. Third, it allows variation. Copying isn't perfect, and occasional errors introduce mutations that create the genetic diversity necessary for evolution. But DNA is not unique in performing these functions. Scientists have created synthetic alternatives called XNAs, xenonucleic acids, that can store information, be copied, and undergo evolution despite having different chemical structures than DNA. These molecules use different sugars in their backbones, 3 O's instead of deoxyribose, locked nucleic acids with modified sugars, or even molecules with completely different backbone structures. These XNAs can form base pairs, store sequences of information, and be replicated by specialized enzymes. They demonstrate conclusively that DNA is not the only possible genetic molecule, merely the one that happened to work on Earth. The chemistry of DNA is optimized for Earth's conditions. DNA is stable in liquid water at temperatures roughly between 0 and 40 degrees Celsius, the temperature range where most Earth life operates. The hydrogen bonds holding the 2 strands together are strong enough to keep the double helix intact, but weak enough that the strands can be separated for copying. The sugar-phosphate backbone is stable in water at neutral pH, but can be broken down by enzymes when necessary. The bases, adenine, thymine, guanine, and cytosine, are moderately stable molecules that can withstand normal cellular conditions, but can be damaged by extreme heat, intense radiation, or strongly acidic or alkaline environments. On a planet with very different conditions, DNA might not function well or at all. Consider a world much hotter than Earth, perhaps a planet orbiting very close to its star, with surface temperatures exceeding 100 degrees Celsius, but with liquid water kept stable by extreme atmospheric pressure. At these elevated temperatures, DNA becomes increasingly unstable. The hydrogen bonds holding the 2 strands together weaken and break more easily. The chemical bonds in the bases and the backbone break down more rapidly. Organisms on such a world would need genetic molecules more heat-resistant than DNA, perhaps with stronger chemical bonds, more stable base structures, or completely different architectures that maintain integrity at high temperatures. Some Earth organisms that thrive in extreme heat have evolved DNA repair mechanisms that constantly fix damage to their genetic material, but there are limits to how hot DNA can tolerate. Beyond a certain temperature, the rate of damage exceeds the capacity of repair mechanisms to fix it. Alien life on a hot world might evolve an alternative genetic molecule with inherently greater thermal stability, perhaps using bases with stronger bonding, or sugars that resist thermal degradation, or entirely different building blocks that remain stable at temperatures where DNA would fall apart within seconds. At the opposite extreme, very cold worlds present different challenges. DNA becomes more rigid at low temperatures, making it harder to separate the strands for copying. The enzymes that copy DNA become less efficient or stop working entirely when too cold. Life on an extremely cold world, perhaps on a moon like Titan, where temperatures hover around -180 degrees Celsius, would need genetic molecules that remain flexible and functional at these frigid temperatures. The chemistry would necessarily be different from DNA, which was shaped by evolution to function in Earth's moderate temperature range. The solvent environment profoundly affects what genetic molecules are possible. DNA functions in liquid water, and its chemical properties are specifically suited to aqueous environments. The sugar phosphate backbone is hydrophilic, attracted to water, which helps keep DNA dissolved in cellular fluids. The bases are hydrophobic, repelled by water, which helps drive base pairing by pushing bases toward each other and away from the surrounding water. This balance creates DNA's structure and stability. In a different solvent, liquid methane, liquid ammonia, or something even more exotic, DNA's chemistry wouldn't work the same way. Water's polarity, its hydrogen bonding capacity, its ability to dissolve certain substances while excluding others. All these properties shape how DNA behaves. In liquid methane, a non-polar solvent, molecules that are hydrophobic in water might become soluble, while hydrophilic molecules might be insoluble. A genetic molecule designed for a methane-based solvent would need completely different chemical properties than DNA, perhaps with non-polar groups exposed to interact with the methane solvent, and polar groups hidden in the molecule's interior. The availability of raw materials constrains what genetic molecules can be built. DNA requires phosphorus, nitrogen, carbon, oxygen, and hydrogen. Phosphorus, though essential for DNA's backbone, is relatively rare in the universe compared to lighter elements. A planet poor in phosphorus might not be able to build DNA-like molecules and would need to evolve genetic systems based on more abundant elements. Perhaps silicon could replace phosphorus in the backbone, or sulfur could play a role, or arsenate, a chemical similar to phosphate, might substitute. Though experiments with arsenate-based DNA on Earth showed it's much less stable than normal DNA. The 4-base system used by DNA, adenine, thymine, guanine, and cytosine, is not the only possible coding scheme. RNA, DNA's chemical cousin, uses uracil instead of thymine, demonstrating that the specific bases aren't fixed. In principle, genetic molecules could use 3 bases, or 6, or even more. More bases would allow more information to be encoded in shorter sequences. With 4 bases, each position in the sequence can encode 2 bits of information, but with 8 bases, each position could encode 3 bits. An alien genetic system might use more or fewer bases depending on what works best with its chemistry. Some scientists have even created expanded genetic alphabets, DNA-like molecules with additional base pairs beyond the natural 4. These synthetic genetic systems can store more information per unit length than natural DNA and can be copied by modified enzymes. The existence of these expanded alphabets demonstrates that the 4-base system is not uniquely optimal, but rather reflects the specific chemistry that evolved on Earth. Alien life might independently evolve genetic systems with different numbers of bases encoding information in different ways. The structure of the genetic molecule might differ radically from DNA's double helix. DNA forms a helix because of how the bases pair and how the sugar phosphate backbone bends, but other structures are possible. Some XNAs form helices with different geometries, left-handed instead of right-handed, wider or narrower than DNA, with more or fewer base pairs per helical turn. Some synthetic genetic molecules don't form helices at all, but adopt completely different 3-dimensional structures. An alien genetic molecule might be a triple helix, a quadruple helix, a ladder without a twist, or some topology we haven't imagined. The copying mechanism might also differ. DNA is copied by enzymes called polymerases that move along the DNA strand, reading the sequence and creating a complementary new strand. This process requires a complex molecular machinery that evolution has refined over billions of years on Earth. Alien life might evolve completely different copying mechanisms, perhaps catalytic RNA-like molecules that copy themselves without protein enzymes, or inorganic crystals that template the formation of complementary structures, or even copying processes that don't involve template-directed synthesis at all, but rather some form of self-assembly guided by the genetic molecule structure. The rate of mutation, how often copying errors occur, affects evolution's pace. DNA polymerases on Earth make errors at a rate of roughly 1 mistake per billion bases, copied for the most accurate enzymes, though rates vary. This error rate is low enough to preserve genetic information across generations, but high enough to generate the variation necessary for evolution. Alien genetic systems might have very different error rates. A system with much lower error rates would evolve more slowly, potentially making adaptation difficult. A system with higher error rates might generate variation faster, but risk genetic information degradation. The optimal error rate depends on generation time, selection pressure, and environmental stability. RNA represents an alternative genetic molecule that exists on Earth and might have preceded DNA in evolution. RNA can store information, catalyze chemical reactions, and replicate all functions DNA cannot perform alone. The RNA world hypothesis proposes that early life used RNA as both genetic material and catalytic molecule before DNA and proteins evolved. An alien world might develop life that remains in an RNA world-like state, never evolving DNA, or might evolve RNA into forms more sophisticated than anything on Earth, creating genetic systems based on elaborate RNA structures rather than DNA. Some scientists have speculated about non-molecular genetic systems. Perhaps information could be stored in the crystal structure of inorganic minerals, with patterns of inclusions, defects, or layering encoding information that could be replicated when crystals grow and form templates for new crystals. Or perhaps information could be stored in magnetic domains in iron-rich minerals, with the orientation of magnetic fields encoding genetic instructions. These ideas are highly speculative and face enormous challenges. How would such systems be read and translated into functional structures? But they illustrate that genetic information storage might not require organic molecules at all. The universality of certain aspects of information storage might transcend specific chemistry. Any genetic system, whether based on DNA, XNA, RNA, or something entirely different, must be able to store discrete, sequential information, symbols arranged in order that can be read and interpreted. This is fundamentally a problem of information theory rather than chemistry. The specific physical substrate that stores the information might be less important than the information itself, and the mechanisms for reading, copying, and translating it into functional structures. If we ever detect alien life, determining its genetic system would be among the first questions we'd want to answer. If alien life uses DNA with the same 4 bases and same genetic code as Earth life, it would suggest either that DNA is universally optimal, unlikely given all the possible alternatives, or that Earth life and alien life share a common origin, perhaps through panspermia. The hypothesis that life can spread between worlds via meteorites or comets. Finding alien life with completely different genetic molecules would confirm that life can independently originate using different chemistry, revealing that DNA is merely one solution among many to the problem of heredity. The genetic code, the mapping between base sequences and amino acids, might also differ. Earth's genetic code is nearly universal across all life, with 3 base sequences called codons specifying which amino acid to insert when building proteins. But the specific assignment of codons to amino acids appears somewhat arbitrary. There's nothing inherent in the chemistry of the codon UUU that demands it code for the amino acid phenylalanine rather than some other amino acid. The code seems to be a frozen accident. Once it was established early in evolution, changing it would be catastrophic because it would alter the meaning of every gene, so it became locked in place. Alien life would likely evolve a completely different genetic code, with different codon assignments, and possibly even a different codon length. 2 base codons, or 4 base codons, or variable length codons. Why alien life might not use DNA comes down to DNA being a solution specific to Earth's conditions: liquid water at moderate temperatures, specific pH ranges, availability of particular elements, and the accidents of chemical evolution that occurred during life's origin on our world. Different conditions would favour different molecules, and even similar conditions might allow evolution to discover different solutions. DNA is remarkable and elegant, but it's not magic or inevitable. It's chemistry, sophisticated, evolved chemistry that works beautifully on Earth, but that represents just one possible answer to the fundamental question of how to store, copy, and transmit genetic information across generations. Across the universe, life might employ countless different genetic systems, each one adapted to its world's unique conditions, each one encoding information and enabling heredity through different molecular mechanisms, proving that while the principle of heredity might be universal wherever life exists, the specific molecular machinery implementing that heredity can vary as widely as the diversity of worlds themselves, with DNA being merely Earth's particular solution to the universal challenge of passing genetic information from parent to offspring through the generations. Why alien life might be microscopic. When we imagine alien life, our minds often conjure images of intelligent beings piloting spacecraft, complex organisms with eyes and limbs exploring alien landscapes, or at minimum, creatures we could observe and recognize as alive. But this expectation might be profoundly misguided. Earth's history offers a sobering perspective. For roughly 3 billion of the 4 billion years that life has existed on our planet, all organisms were microscopic. Bacteria, archaea, and single-celled eukaryotes dominated Earth's biosphere for the vast majority of life's history. Complex multicellular organisms, plants, animals, fungi, are recent arrivals, having existed for less than 1 billion years. If Earth's timeline is any indication, most life in the universe might be microscopic, existing as single cells or simple colonies that never evolve into the complex macroscopic forms we're accustomed to seeing. The transition from single-cell to multicellular life represents one of the most difficult evolutionary innovations in Earth's history. It only happened once in the bacterial lineage, never successfully transitioning beyond simple filaments and colonies, and only a few times in the eukaryotic lineage, producing plants, animals, and fungi. This rarity suggests that while single-celled life might emerge relatively easily wherever conditions permit, the evolution of complex multicellularity requires specific circumstances that might not commonly occur. Many alien worlds might develop thriving microbial biospheres that remain forever microscopic because the evolutionary innovations needed for large, complex organisms never occur. Energy availability represents the first major constraint on complexity. Complex multicellular organisms require substantial energy to build and maintain their bodies. They need energy to power specialized organs, to move through their environments, to grow to large sizes. Most of this energy ultimately comes from oxygen-based metabolism, which releases far more energy per molecule of food than anaerobic metabolism does. The efficiency of oxygen metabolism, about 15 times more energetic than the best anaerobic alternatives, enabled the evolution of large active organisms on Earth. But oxygen was not always available in Earth's atmosphere. For the first 2 billion years or more of life's existence, the atmosphere contained very little free oxygen. Life during this time remained entirely microscopic and relatively simple, constrained by the low energy yields of anaerobic metabolism. Only after photosynthetic bacteria evolved and began producing oxygen as a waste product did atmospheric oxygen accumulate, and only after oxygen reached substantial levels could organisms evolve the high-energy metabolisms necessary for large size and complexity. Many alien worlds might never undergo this transition. If photosynthetic life never evolves, or if it evolves but produces different waste products, perhaps using electron donors other than water that don't release oxygen, the atmosphere might remain oxygen poor indefinitely. Life on such worlds would be permanently restricted to anaerobic metabolism, with its inherent energy limitations preventing the evolution of large complex organisms. The biosphere might flourish with countless microscopic species filling every available niche, but nothing larger than perhaps a millimeter would ever evolve, because the energy budgets of anaerobic metabolism cannot support larger sizes or more complex structures. Predation drives much of the evolution toward complexity on Earth. The development of predators created selection pressure for prey to evolve defenses, armor, toxins, multicellularity that makes them too large to be consumed by single-celled predators. Predators, in turn, evolved mechanisms to overcome these defenses: better sensing systems, faster movement, cooperative hunting. This evolutionary arms race between predators and prey drove increasing complexity, with both sides becoming more sophisticated over generations. The transition to multicellularity in animals might have been driven at least partially by predation pressure from other single-celled organisms. On an alien world where predation never becomes significant, perhaps because environmental conditions don't favor the evolution of heterotrophs, or because chemical energy is so abundant that organisms don't need to consume each other, this driver of complexity would be absent. Life might remain a collection of bacteria-like organisms metabolizing chemicals from their environment, with no selection pressure favoring the evolution of larger, more complex forms. Without predation or competition driving an evolutionary arms race, the biosphere might reach an equilibrium of simple, efficient microorganisms that persist unchanged for billions of years. The evolution of eukaryotic cells, cells with nuclei and complex internal structures, required an extraordinarily unlikely event called endosymbiosis, where one cell engulfed another, and instead of digesting it, established a permanent symbiotic relationship. On Earth, mitochondria, the energy-producing organelles in eukaryotic cells, originated as free-living bacteria that were engulfed by other cells and eventually became integrated parts of those cells. This event, which happened roughly 2 billion years ago, was apparently unique in Earth's history. It happened once, and all eukaryotic cells descend from that single event. Eukaryotic cells made complex multicellular life possible. Their mitochondria provide far more energy per cell than bacteria can generate, allowing cells to support larger genomes and more complex structures. Their internal compartmentalization allows specialized biochemistry to occur in different cellular regions. Their complex cytoskeletons enable intricate cell shapes and coordinated movements. Without eukaryotic cells, complex multicellular organisms probably could not evolve. If endosymbiosis was difficult, requiring very specific circumstances to occur even once on Earth, alien worlds might never undergo this transition. Life might remain forever bacterial, lacking the cellular complexity necessary as a foundation for multicellular organisms. These worlds would have rich microbial ecosystems, with tremendous diversity at the microscopic level, but would never produce organisms visible to the naked eye. Environmental stability influences evolutionary innovation. Earth's environment has been highly variable over geological time. Ice ages, warming periods, asteroid impacts, volcanic catastrophes, changing atmospheric composition, continents drifting and colliding. These environmental changes created selection pressures that favored adaptability and innovation. Mass extinctions wiped out dominant groups, allowing new forms to radiate and diversify. Without such disruptions, dominant organisms might remain unchanged indefinitely, never facing circumstances that favor more complex alternatives. An alien world with a remarkably stable climate and environment over billions of years might never see complex life evolve. Early microbial ecosystems might reach an equilibrium where existing organisms are so well adapted to unchanging conditions that no complex innovations provided advantages. Microbes would efficiently fill every niche, processing every available chemical, extracting every erg of available energy, and no evolutionary pressure would favor the metabolically expensive transition to larger, more complex forms. The planet would remain microbial forever, not because complex life is impossible, but because stable conditions never create circumstances where complexity is advantageous. The availability of ecological niches affects diversification. On Earth, new environmental niches continuously opened as continents drifted, climates changed, and oxygen accumulated in the atmosphere. Moving onto land created entirely new sets of niches, terrestrial environments with different challenges than aquatic ones. Flying created another set of niches. Each new opportunity drove adaptive radiations where organisms evolved to exploit newly available resources and habitats. A planet lacking this niche diversity might not provide opportunities for complex life to evolve. A world completely covered by ocean with no land would lack terrestrial niches. A world with a homogeneous environment, perhaps a global ocean with uniform temperature and chemistry from pole to pole, would offer fewer distinct niches than Earth's highly varied environments. With fewer niches available, there would be less opportunity for adaptive radiation and less selection pressure driving organisms toward the specializations and complexities that fill diverse ecological roles. Timescales matter significantly. Evolution proceeds through random mutations and natural selection, accumulating beneficial changes over countless generations. Complex innovations require many individual evolutionary steps, each one building on previous changes. The evolution of eyes, for instance, required the initial evolution of light-sensitive proteins, then the gathering of these proteins into light-sensitive patches, then the invagination of these patches into cups that provide directional information, then the development of lenses that focus light, then the neural processing systems to interpret visual information. Each step took many generations and many mutations. On an alien world where organisms have very long generation times, perhaps living for thousands of years before reproducing, evolution would proceed extraordinarily slowly. A complex innovation that might evolve in tens of millions of years on Earth, where many organisms reproduce annually or even faster, might take billions of years on a world where generation times are measured in millennia. If the planet star has a relatively short lifetime, perhaps a massive star that will exhaust its fuel in a few billion years, there might simply not be enough time for complex life to evolve before the star's death sterilizes the planet. The chemical environment limits biological complexity. Complex organisms require diverse biochemistry, proteins for structure and catalysis, lipids for membranes, nucleic acids for information storage, carbohydrates for energy and structure. Building these diverse molecules requires access to various elements in appropriate forms. A planet poor in essential elements, perhaps lacking sufficient phosphorus, nitrogen, sulfur, or trace metals, might not provide the chemical building blocks necessary for complex biochemistry. Life might arise using simpler chemistry, but might be unable to evolve the molecular diversity needed for complex cells and multicellular structures. Physical constraints on size affect what complexity is possible. Surface tension becomes increasingly important at small scales. For microscopic organisms living in water, surface tension is a significant force. Water behaves more like thick syrup than like the thin fluid humans experience. Moving through water at microscopic scales requires different strategies than swimming at macroscopic scales. These physical differences mean that microorganisms experience a fundamentally different physical world than large organisms, and the adaptations that work well at microscopic scales might not scale up successfully. The speed of light sets absolute limits on how quickly information can be transmitted within an organism. For microscopic cells, this is never a constraint. Signals cross the cell in negligible time. But as organisms grow larger, signal transmission times become significant. A 1-meter organism experiences light travel times of about 3 nanoseconds, still essentially instantaneous for chemical and neural signals. But organisms must coordinate their parts, and this coordination becomes more difficult as size increases. Neural signals in humans travel at speeds of about 100 meters per second, meaning signals take milliseconds to travel from extremities to brain. For a hypothetical organism many meters or kilometers in size, coordination would become increasingly difficult. Detection bias affects our perception of what life looks like. Humans evolved to perceive objects roughly our own size. We see animals, plants, and landscape features easily because our sensory systems are optimized for that scale. Microscopic organisms are invisible without technological assistance. An alien observer visiting Earth equipped with sensing systems similar to human vision might conclude that Earth has relatively little life, missing entirely the vast microbial world that actually dominates in terms of biomass, diversity, and metabolic activity. Similarly, when we search for alien life, our methods tend to focus on detecting macroscopic effects, oxygen in atmospheres produced by photosynthetic organisms, changes in planetary albedo from vegetation, perhaps even artificial lights from technological civilizations. A planet covered in microbial life, producing no oxygen, with no multicellular organisms, with nothing visible at planetary scales, might appear lifeless to our telescopes, even if it hosts an incredibly rich and diverse microbial biosphere. Statistical considerations based on Earth's history suggest that if we discovered alien life, it would most likely be microscopic. Life existed on Earth for about 3 billion years before complex multicellular organisms evolved. If we randomly selected a moment in Earth's history, there would be a roughly 75% chance of finding only microscopic life. Assuming Earth's timeline is typical, which may or may not be true, most inhabited planets at any given time would be in their microbial phase, with complex life being relatively rare. Why alien life might be microscopic comes down to microbial life being easy to achieve relative to complex life, requiring only basic metabolism, reproduction, and evolution, while complex life requires numerous specific evolutionary innovations. Oxygenic photosynthesis, or equivalent high-energy metabolism, eukaryotic cells with their mitochondrial endosymbionts, multicellularity with coordinated cells working together, specialized tissues and organs, each one potentially rare or slow to evolve. Many worlds might develop thriving microbial ecosystems within their first billion years, but might never progress beyond that stage, remaining forever inhabited by bacteria-like organisms invisible to the naked eye, yet representing the most common form of life in the universe. a cosmos filled not with civilizations or even visible organisms, but with countless worlds hosting microbial biospheres that flourish in every conceivable environment, from sunlit surface waters to deep subsurface rocks, from hydrothermal vents to subsurface oceans beneath ice, each microscopic cell representing a success story of evolution in its own right, reminding us that complexity and large size are not prerequisites for biological success, and that if we ever detect life beyond Earth, we should not be disappointed if it consists of nothing more than microbes, because microbial life might be life's most common, most successful, most enduring form across the vast expanse of the living universe. Why nothing can go faster than light. Light moves at exactly 300,000 kilometers per second in a vacuum, fast enough to circle Earth more than 7 times in a single second. This speed seems arbitrary at first, just another number to memorize. But the speed of light represents something far more profound than a mere velocity. It's a fundamental limit built into the structure of the universe itself, a cosmic speed limit that nothing with mass can reach, let alone exceed. Understanding why nothing can go faster than light means understanding one of the most revolutionary insights in physics, that space and time are not separate, unchanging backdrops to events, but are woven together into a unified fabric that behaves in deeply counterintuitive ways. Before Albert Einstein published his special theory of relativity in 1905, most physicists assumed that velocities simply added together in straightforward ways. If you're on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour relative to the train, then someone standing beside the tracks would see the ball moving at 70 kilometers per hour. This common sense addition of velocities works perfectly well at everyday speeds. But Einstein realized that this intuitive picture breaks down at velocities approaching the speed of light, and the breakdown reveals something fundamental about the nature of space and time. Einstein started with 2 basic principles. First, the laws of physics should be the same for everyone moving at constant velocity, regardless of how fast they're going. This principle of relativity had been around since Galileo, and it accords with common experience. You can't tell from experiments done inside a smoothly moving train whether the train is moving or the station is moving past you. Second, and more radically, Einstein proposed that the speed of light is the same for everyone, regardless of how fast they're moving or how fast the light source is moving. This second principle contradicts our everyday intuition about velocity addition. If you're on a train moving forward and you shine a flashlight forward, you might expect someone on the platform to measure the light going faster than someone on the train would measure it, by an amount equal to the train's speed. But experiments repeatedly showed that this doesn't happen. The person on the platform and the person on the train both measure exactly the same speed for the light. This bizarre result seems impossible if we assume that space and time are absolute and unchanging. Einstein's breakthrough was realizing that space and time must not be absolute. Instead, they must adjust themselves to keep the speed of light constant for all observers. When you move faster, time actually slows down for you relative to someone standing still, and distances contract in your direction of motion. These effects, called time dilation and length contraction, are not optical illusions or measurement errors. They're real physical changes in how time flows and how space extends. At everyday speeds, these relativistic effects are incredibly tiny, too small to notice. A person traveling in a car at highway speed experiences time flowing more slowly than someone standing still, but the difference amounts to only billionths of a second over a lifetime. But as speeds approach the speed of light, these effects become dramatic. At 90% of light speed, time runs at only about 44% of the normal rate. At 99% of light speed, time runs at about 14% of normal. As you get closer and closer to light speed, time slows down more and more dramatically, approaching a complete stop as velocity approaches the speed of light. This time, dilation has been confirmed through countless experiments. Atomic clocks flown on airplanes run slightly slower than identical clocks left on the ground, by exactly the amount Einstein's equations predict. Particles called muons, created when cosmic rays strike the upper atmosphere, live for only about 2 microseconds before decaying. At the speeds they travel, close to the speed of light, time dilation extends their lifetimes enough that they reach the ground before decaying, something that would be impossible if time flowed normally for them. GPS satellites must account for relativistic time dilation, both from their speed and from Earth's gravity, or they would accumulate errors of several kilometers per day. Length contraction is equally real. A spaceship traveling at 99% of light speed would be compressed to about 14% of its rest length in the direction of motion from the perspective of someone watching it pass by. From the crew's perspective, inside the ship, they wouldn't feel compressed. They would measure their ship as having its normal length, but they would measure the distance to their destination as being contracted, appearing much shorter than it does to someone at rest relative to the destination. These strange effects arise from the fact that the speed of light must be the same for everyone. If you're chasing a beam of light at 99% of light speed, you still measure that light beam as moving away from you at full light speed, not at 1% of light speed, as you might expect. This only makes sense if time is flowing more slowly for you, and distances are contracted in your reference frame. The adjustments exactly compensate to keep the speed of light constant. But what happens if you try to accelerate something to light speed? Here's where the cosmic speed limit becomes absolute. As an object with mass accelerates, it gains kinetic energy. In classical physics, kinetic energy depends on velocity in a simple way. Double the velocity, and kinetic energy increases by a factor of 4. But Einstein showed that the relationship changes as you approach light speed. The energy required to accelerate an object increases more and more dramatically as velocity increases, and as you approach light speed, the energy required approaches infinity. This happens because of something called relativistic mass increase. As an object moves faster, it becomes harder to accelerate. It behaves as if it's getting more massive. At 90% of light speed, an object has about twice its rest mass. At 99%, it has about 7 times its rest mass. As velocity approaches light speed, the relativistic mass approaches infinity. To actually reach light speed would require infinite energy to accelerate infinite mass, a physical impossibility. Light itself travels at light speed because photons, the particles of light, have no mass. Maxwell's equations, which describe how electromagnetic fields behave, predict that electromagnetic waves travel at a specific speed determined by properties of space itself. Einstein realized that this speed is the cosmic speed limit, and that massless particles must travel at exactly this speed. Photons don't have to accelerate to light speed. They're created already moving at light speed, and they can never slow down or stop as long as they exist. Other massless particles like gluons, which carry the strong nuclear force, also travel at light speed. Gravitational waves, ripples in space-time itself, travel at light speed as well. Mass is what prevents particles from reaching this ultimate speed. Any particle with mass can approach light speed arbitrarily closely if given enough energy, but can never quite reach it. The relationship between energy, mass, and velocity is captured in Einstein's famous equation, E equals mc squared, though this is actually a special case of a more general equation. The full equation shows that total energy equals the rest mass energy plus kinetic energy, and as velocity increases, more and more of the total energy goes into the kinetic energy component. At very high velocities, most of the energy is kinetic rather than rest mass. Particle accelerators demonstrate these principles directly. The Large Hadron Collider accelerates protons to more than 99 0.99% of light speed. At these velocities, the protons have about 7,000 times more energy than their rest mass energy. Accelerating them to even higher velocities, getting closer to light speed, requires exponentially more energy for each incremental increase in velocity. No matter how much energy you put in, the protons never quite reach light speed, and the energy required to actually reach it would be infinite. Some people wonder whether traveling faster than light might be possible by warping space rather than moving through it. General relativity does allow for exotic spacetime geometries, like wormholes or warp drives, that could theoretically allow effective faster-than-light travel without actually moving through space faster than light. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a theoretical way to contract space in front of a spacecraft and expand it behind, allowing the spacecraft to effectively travel faster than light while locally moving slower than light relative to the space immediately around it. However, these solutions require exotic matter with negative mass or negative energy density, properties never observed and possibly forbidden by quantum mechanics. Even if such matter could exist, the energy requirements would be astronomical, potentially requiring more energy than exists in the entire observable universe. These remain purely theoretical concepts, with no practical pathway to implementation, and they don't violate the fundamental principle that nothing can move through space faster than light. The cosmic speed limit has profound implications for space travel. Even at light speed, it would take over 4 years to reach the nearest star beyond our Sun, Proxima Centauri. Travelling to the centre of our galaxy would take over 25,000 years at light speed. Reaching nearby galaxies would take millions of years. The vast distances between stars and galaxies, combined with the absolute speed limit, mean that interstellar travel remains extraordinarily challenging even in principle. For travellers moving at near light speeds, time dilation provides a partial solution. From the crew's perspective, a journey might take only months or years while decades or centuries pass on Earth. This time, dilation allows relativistic travellers to cross vast distances within their own lifetimes, though everyone they knew would age far more or be long dead by the time they returned. This creates a fundamental asymmetry. The traveller's time and the stay-at-home's time flow at different rates, and there's no way to make them match up again. The speed of light also limits how quickly information can travel. When you see a star in the night sky, you're seeing it as it was years or centuries ago. That's how long the light took to reach you. The sun you see is 8 minutes in the past. If the sun suddenly vanished, we wouldn't know for 8 minutes. This light travel time creates what physicists call a light cone, the boundary between events that can influence you and events that cannot because they're too far away in space and too close in time for light to have travelled from there to here. Causality itself depends on the cosmic speed limit. If information could travel faster than light, it would be possible to send messages backward in time, to communicate with your own past. This creates logical paradoxes, like sending a message to your past self, telling yourself not to send the message. The speed of light limit prevents these paradoxes by ensuring that cause always precedes effect for all observers, regardless of their motion. The universe seems designed in a sense with this speed limit built in. Light speed isn't just the speed at which light happens to travel, it's a fundamental property of space-time itself, woven into the structure of reality. Mass is what prevents particles from reaching this ultimate speed, and the closer you get to it, the more energy is required to go faster, asymptotically approaching infinite energy at the limit. This speed limit connects space and time in an intimate way. Space and time aren't separate entities but are aspects of a unified, four-dimensional space-time. Events that appear simultaneous to one observer might not be simultaneous to another observer moving differently. The cosmic speed limit defines the structure of this space-time, determining how space and time mix together as observers change velocity. Why nothing can go faster than light ultimately comes down to the structure of spacetime itself. The speed of light isn't a speed limit in the sense of a rule imposed from outside. It's a fundamental property of how the universe is built, how space and time relate to each other, and how energy and mass behave. Reaching light speed would require infinite energy. The only things that can travel at light speed are things with no mass, like photons, which must always travel at this speed. Everything else, everything with mass, can only approach this ultimate velocity, forever accelerating, but never quite reaching the cosmic speed limit that defines the maximum rate at which anything can travel through the fabric of spacetime. Why moons orbit in perfect circles? When you look at diagrams of moons orbiting planets, they're often depicted as perfect circles with the planet at the center. This image is actually misleading. No moon orbits in a perfect circle. Every orbit in the universe, whether it's a moon around a planet around a star, or a star around a galaxy's center, follows an ellipse, a stretched circle, with the central body at one of the ellipse's two focal points, not at the center. However, many moon orbits are remarkably close to circular, so nearly circular that the deviation is barely noticeable. Understanding why some moons have nearly circular orbits, while others follow elongated ellipses, means understanding orbital mechanics, tidal forces, and the long-term evolution of gravitational systems. The fundamental laws governing orbital motion were discovered by Johannes Kepler in the early 17th century, based on meticulous observations of planetary positions compiled by Tycho Brahe. Kepler's first law states that planets orbit the Sun in ellipses, with the Sun at one focus. This applies equally to moons orbiting planets. An ellipse is characterized by its eccentricity, a number between 0 and 1. An eccentricity of 0 represents a perfect circle. An eccentricity close to 0 represents a nearly circular ellipse. Higher eccentricities produce more elongated ellipses, and an eccentricity of 1 represents a parabola, an open curve, not a closed orbit at all. Earth's moon has an orbital eccentricity of about 0.0549, meaning its orbit is quite close to circular but noticeably elliptical. At its closest approach, called perigee, the moon is about 363,000 kilometers from Earth. At its farthest point, called apogee, it's about 405,000 kilometers away, a difference of about 42,000 kilometers, or roughly 11%. This variation causes the moon's apparent size in Earth's sky to change noticeably over the course of a month. A full moon at perigee appears about 14% larger in diameter than a full moon at apogee, the so-called supermoon phenomenon. Many other moons have far more circular orbits than Earth's moon. Jupiter's major moons, the Galilean satellites Io, Europa, Ganymede, and Callisto, all have very low eccentricities. Io's eccentricity is about 0.0041, Europa's is 0.009, Ganymede's is 0.0013, and Callisto's is 0.0074. These are remarkably circular orbits, with the differences between closest and farthest approaches being only tiny fractions of the orbital radius. Saturn's largest moon, Titan, has an eccentricity of 0.0288, still quite circular, though less so than Jupiter's major moons. The reason many moons approach circular orbits lies in tidal forces and the dissipation of energy over time. When a moon orbits a planet on an elliptical path, its distance from the planet changes continuously. As the distance changes, so does the strength of the tidal forces between the planet and moon. Tides work both ways. The moon raises tides on the planet, and the planet raises tides on the moon. These tidal bulges require energy to create because they deform the bodies involved, flexing and stretching them. For a moon in an eccentric orbit, the tidal bulges change in size as the moon moves closer to and farther from the planet. This continuous flexing dissipates energy as heat through internal friction, the same mechanism that makes a rubber ball warm up when you repeatedly squeeze and release it. This tidal heating is not a small effect. Jupiter's moon, Io, experiences such intense tidal heating due to its slightly eccentric orbit that it's the most volcanically active body in the solar system, with lava lakes, erupting volcanoes, and a surface constantly renewed by volcanic activity. The energy dissipated through tidal heating doesn't disappear. It comes from the orbital energy of the moon. As orbital energy is lost, the characteristics of the orbit change. Specifically, the eccentricity decreases. The orbit becomes more circular. This process, called tidal circularization, operates on timescales of millions to billions of years, gradually transforming elliptical orbits into nearly circular ones. The timescale depends on the masses involved, the distances, the physical properties of the bodies, how easily they deform, and the initial eccentricity. Earth's moon provides a clear example of tidal evolution, though in the moon's case the effect is primarily in the exchange of angular momentum rather than circularization. The moon raises tides on Earth, the familiar ocean tides that rise and fall twice daily. Earth's rotation carries these tidal bulges slightly ahead of the Earth-Moon line because of friction and the time it takes for water to respond to the tidal forces. This offset means the tidal bulges pull on the moon, accelerating it in its orbit and causing it to gradually move away from Earth at about 3.8 centimeters per year, a rate precisely measured by bouncing laser beams of retroreflectors left on the moon by Apollo astronauts. As the moon moves outward, Earth's rotation slows down to conserve angular momentum. Earth's day gradually lengthens, currently by about 1.7 milliseconds per century. This process has been operating for billions of years. Early in Earth's history, when the moon was much closer, tidal forces were far stronger. Days were much shorter, perhaps only 5 to 6 hours, and the moon orbited much faster and on a more eccentric orbit. Over billions of years, tidal forces circularized the moon's orbit to its current low, but non-zero eccentricity. The moon's orbital eccentricity isn't zero because the circularization process hasn't completed and perhaps never will. The sun's gravitational pull perturbs the moon's orbit, periodically increasing its eccentricity slightly. These perturbations compete with the tidal circularization, creating a balance that maintains a small but non-zero eccentricity. Additionally, the ultimate end state of tidal evolution is tidal locking, where the moon always shows the same face to the planet, and the planet's rotation period equals the moon's orbital period. Earth's moon is already tidally locked to Earth, but Earth is not locked to the moon. Eventually, if given enough time, Earth would become locked to the moon as well, with both bodies always showing the same faces to each other, though this would take tens of billions of years, longer than the sun's remaining lifetime. Some moons maintain eccentric orbits despite tidal forces because of orbital resonances with other moons. Jupiter's moons Io, Europa, and Ganymede are locked in a 1 to 2 to 4 resonance. For every orbit Ganymede completes, Europa completes 2, and Io completes 4. This resonance was discovered by Pierre-Simon Laplace in the 18th century. The gravitational interactions in this resonance maintain Io's and Europa's orbital eccentricities even as tidal forces try to circularize them. The result is continuous tidal heating, keeping Io's interior molten and likely maintaining a subsurface ocean on Europa beneath its icy crust. Saturn's moon, Enceladus, experiences similar effects. Its orbital eccentricity of about 0.0047 seems small, but it's sufficient to generate significant tidal heating in this small moon. Enceladus orbits in a 2-to-1 resonance with the larger moon Dione. The resonance prevents the orbit from fully circularizing, maintaining just enough eccentricity to produce tidal heating that keeps a subsurface ocean liquid beneath Enceladus's southern polar region. Geysers of water erupt through cracks in the ice, spraying material into space and creating Saturn's E-ring. New moons in eccentric orbits take time to circularize. If a moon forms from a giant impact, as Earth's moon likely did, the debris initially orbits in highly eccentric, chaotic paths. Over time, collisions between orbiting fragments dissipate energy and circularize the orbits, while material gradually coalesces into a single moon. The moon starts with a moderately eccentric orbit that gradually becomes more circular through tidal interactions. Young moons should have more eccentric orbits than old moons, all else being equal. Captured moons often retain eccentric orbits. When a planet gravitationally captures a passing asteroid or comet, the capture typically results in a highly eccentric orbit. Without significant tidal forces or atmospheric drag to circularize the orbit, it remains eccentric indefinitely. This is why many of the small, irregular outer moons of the giant planets have highly eccentric orbits. They're captured asteroids, or Kuiper belt objects, that have never undergone significant tidal circularization. Mars's two small moons, Phobos and Deimos, are thought to be captured asteroids, though their orbits are fairly circular, suggesting either that they've been in place long enough for tides to act or that they were captured through an unusual mechanism that placed them in nearly circular orbits initially. The mathematical framework for understanding orbital evolution through tides was developed in the 19th and 20th centuries by George Darwin, son of Charles Darwin, and others. The tidal quality factor, denoted Q, quantifies how efficiently a body dissipates tidal energy. Bodies with low Q dissipate energy efficiently, leading to faster orbital evolution. Rocky bodies typically have Q values of 10 to 100. Gas giants have Q values around 10,000 to 100,000 because gases don't maintain permanent tidal bulges as efficiently as solid or liquid bodies. These Q values determine how quickly orbits evolve. Computer simulations of moon system evolution incorporate tidal effects, gravitational interactions between multiple moons, and perturbations from the Sun and other planets. These simulations show that systems naturally evolve toward configurations with circular orbits, tidal locking, and often orbital resonances. The solar system's moon systems we observe today represent billions of years of this evolution, with orbits that have circularized, resonances that have captured moons into stable configurations, and tidal locking that has synchronized rotations. Some moons will never fully circularize their orbits because external perturbations constantly act to increase eccentricity. The moon's orbit around Earth is perturbed by the Sun, creating periodic variations in eccentricity over 27.5-day cycles. Neptune's moon Triton orbits in a retrograde direction, opposite to Neptune's rotation, suggesting it was captured from the Kuiper belt. Triton's orbit has circularized over billions of years to an eccentricity of only 0.000016, one of the most circular orbits known, but the orbit is also slowly decaying. Tidal forces are causing Triton to spiral inward, and in about 3.6 billion years, it will cross Neptune's Roche limit and be torn apart, forming a spectacular ring system. The appearance of circular orbits in diagrams and popular depictions stems from the fact that many major moons genuinely have nearly circular orbits. Eccentricities low enough that drawing the ellipse versus a circle would show barely any difference. For Ganymede, with its eccentricity of 0.0013, the difference between the orbit's longest and shortest diameters is only 0.26%. Drawing this accurately would require extraordinary precision. For practical purposes, these orbits are functionally circular, even though they're technically ellipses. Perfect circles don't exist in orbital mechanics because achieving exactly zero eccentricity requires perfectly balanced initial conditions and no subsequent perturbations, conditions that never occur in nature. But through billions of years of tidal evolution, many moons have achieved orbits so close to circular that they serve as excellent approximations, shaped by the patient, inexorable work of tidal forces, dissipating energy, transforming the chaos of formation into the elegant, nearly circular orbits that characterize mature moon systems throughout the solar system, demonstrating how gravitational interactions over immense timescales can organize and simplify what begins as disorder, creating the stable, predictable, celestial mechanics that allow us to calculate moon positions years or centuries into the future with extraordinary precision. What intelligent alien technology might reveal. The search for extraterrestrial intelligence has focused primarily on listening for radio signals, deliberate transmissions from alien civilizations trying to communicate across the cosmos. Since 1960, when astronomer Frank Drake conducted the first systematic search for alien radio signals in what came to be called Project Ozma, scientists have scanned the sky with increasingly sensitive radio telescopes, hoping to detect patterns in the cosmic static that would indicate intelligent origin. But radio signals represent just one possible technological signature among countless ways that advanced civilizations might make their presence known across interstellar distances. Understanding what intelligent alien technology might reveal means thinking beyond communication attempts to consider the inevitable side effects and engineering projects that any sufficiently advanced civilization would produce. Technology leaves traces. Human civilization has only been producing radio signals for about a century. Yet already, our technological fingerprint extends outward in a sphere over 200 light-years in diameter, expanding at the speed of light. Television broadcasts, radar installations, radio communications, all of this electromagnetic radiation leaks into space, creating a bubble of human-generated signals spreading through the galaxy. An alien civilization with sensitive enough radio telescopes could detect these signals and know that an industrial, technological species exists on Earth, even if we never intentionally try to contact them. Our technology reveals us whether we choose to advertise our presence or not. The same principle applies to alien civilizations. Any technological species using electromagnetic radiation for communication, navigation, or industrial processes would inadvertently create detectable signals. The frequency, pattern, and characteristics of these signals would differ from natural astronomical sources. Natural radio emissions from stars, nebulae, and other cosmic objects tend to be broadband, spread across a wide range of frequencies, or if narrowband, they're produced by specific atomic or molecular transitions at predictable frequencies. Artificial signals, in contrast, might be extremely narrowband, might drift in frequency in patterns that reflect the relative motion of transmitter and receiver, or might contain modulations and patterns that have no natural explanation. The famous WOW signal detected in 1977 by the Big Ear radio telescope at Ohio State University demonstrated what a potential technosignature might look like. For 72 seconds, the telescope received a strong, narrow band signal from the direction of the constellation Sagittarius. The signal was so unusual that astronomer Jerry Amon wrote "Wow" on the printout, giving the detection its name. The signal has never been detected again, despite decades of subsequent observations, and its origin remains unexplained. It might have been terrestrial interference, or a reflection off space debris, or a natural phenomenon we don't yet understand, or it might have been exactly what it appeared to be, a brief, powerful transmission from an alien source that was never repeated. Optical signals represent another detection method. Laser technology on Earth has advanced to the point where powerful lasers could, in principle, outshine the sun at specific wavelengths for brief moments. If we pointed a sufficiently powerful laser at a star An alien astronomer observing from that star system might detect the flash, recognizing it as artificial because of its extreme brightness at a single wavelength. This is the basis for optical SETI, the search for brief intense laser pulses from other civilizations. Aliens might use lasers for interstellar communication because lasers are highly directional and can carry large amounts of information. A civilization intentionally trying to contact other species might beam powerful laser pulses toward nearby stars, hoping someone is watching. But some of the most compelling technosignatures might come not from communication attempts, but from large-scale engineering projects. Any advanced civilization would need energy, and energy requirements grow as civilizations become more technologically sophisticated. In 1964, physicist Freeman Dyson proposed that a sufficiently advanced civilization might construct a vast structure around its star to capture a significant fraction of the star's total energy output. This structure, called a Dyson sphere or Dyson swarm, might consist of countless solar panels, habitats, or other components orbiting the star, intercepting sunlight and converting it to useful energy. A complete Dyson sphere would make the star invisible at visible wavelengths. All the light would be absorbed by the structure, but the structure would glow in infrared radiation, emitting the waste heat from whatever processes the captured energy powered. From a distance, a star surrounded by a Dyson sphere would appear anomalously bright in infrared while being dim or invisible in visible light. Astronomers have searched for such infrared excess stars, cataloguing objects that might be Dyson spheres. Though all candidates discovered so far have more mundane explanations like dust clouds or unusual stellar properties. Megastructures don't need to enclose entire stars to be detectable. A single, enormous structure in orbit around a star might block a tiny fraction of the star's light as it passes in front of the star from our perspective. This would create a transit, a dip in the star's brightness, similar to what happens when a planet transits its star. But while planetary transits follow regular, predictable patterns with consistent depths and durations, a megastructure might create irregular, asymmetric transits that don't match any natural explanation. The star KIC 8462852, also known as Tabby's star after astronomer Tabitha Boyajian, who led the research team that discovered its unusual behavior, demonstrated what such anomalies might look like. This star, observed by the Kepler Space Telescope, exhibited irregular, dramatic dips in brightness, sometimes dropping by more than 20%, that didn't match the patterns expected from planets, dust clouds, or any other standard astronomical explanation. The irregular timing and unusual shapes of the dimming events led some researchers to speculate about megastructures, though most scientists now favour natural explanations involving dust and debris, possibly from a disintegrating comet or planet. Still, Tabby's star showed that we could detect anomalous dimming patterns, and if megastructures exist, similar observations might reveal them. Atmospheric pollution represents a more subtle, but potentially detectable, technosignature. Industrial civilizations inevitably alter their planet's atmosphere through their activities. On Earth, the Industrial Revolution increased carbon dioxide levels, added artificial chemicals like chlorofluorocarbons, and changed atmospheric chemistry in detectable ways. Some proposed technosignatures involve looking for molecules in exoplanet atmospheres that shouldn't exist naturally. Chlorofluorocarbons, for instance, are entirely artificial. They don't form through natural processes, but are produced industrially. Detecting CFCs in an exoplanet's atmosphere would be strong evidence for industrial activity. Similarly, nitrogen dioxide concentrations above natural levels could indicate industrial combustion. Certain combinations of atmospheric gases might indicate technological activity. For example, large amounts of both oxygen and methane in the same atmosphere shouldn't coexist naturally because these gases react with each other. If both are abundant, something must be continuously producing them. While biology can produce both gases, certain ratios or the presence of specific isotopes might point toward industrial rather than biological sources. City lights offer another potential technosignature. Earth's night side is dramatically brighter than it was before artificial lighting, with cities visible from space as brilliant concentrations of light. An alien civilization observing Earth with sufficiently powerful telescopes could detect this artificial illumination, recognizing it as technological in origin because the light spectrum differs from natural phenomena, like forest fires or volcanic activity. The light would also be concentrated in specific patterns, along coastlines, in networks of roads, around population centers, rather than being randomly distributed. Detecting city lights on exoplanets would be extraordinarily challenging with current technology. The light from the planet's star overwhelms the faint glow of artificial lighting by enormous margins. But future telescopes, particularly those designed to directly image exoplanets by blocking the star's light, might have the sensitivity to detect bright illumination on a planet's night side, especially if the civilization uses inefficient lighting that wastes energy as light escaping into space, rather than being directed downward toward the ground. Space-based infrastructure might be detectable through reflected light or occultations. Satellites, space stations, solar panel arrays, and other orbital structures reflect light from their star. A civilization with extensive orbital infrastructure might create a faint cloud of reflected light around their planet, detectable as excess brightness beyond what the planet itself would reflect. Similarly, large orbital structures might occasionally pass in front of stars in the background as seen from Earth, creating very brief, tiny dips in brightness that could be detected through careful monitoring. Propulsion systems represent another potential technosignature. Any civilization attempting interstellar travel would need enormous energy to accelerate spacecraft to significant fractions of light speed. Some proposed propulsion systems would create detectable signatures. Nuclear pulse propulsion, using nuclear explosions for thrust, as proposed in the Orion project, would create distinctive radiation signatures. Antimatter engines would produce gamma rays from matter-antimatter annihilation. Fusion drives would create specific spectral signatures from the fusion reactions. Even laser-pushed light sails, sails accelerated by powerful lasers from the home star system, would create bright laser beams visible across interstellar distances to anyone positioned along the beam's path. Gravitational engineering, if possible, might create detectable anomalies. If advanced civilizations can manipulate gravity or space-time, something beyond our current technological capabilities, but not necessarily forbidden by physics, their activities might create detectable effects. Artificial gravitational waves at unusual frequencies, anomalous motions of stars or planets that suggest artificial manipulation, or regions of space with unexplained gravitational properties could all potentially indicate advanced technology at work. Asteroid mining and large-scale resource extraction would alter the appearance of solar systems. A civilization mining asteroids for raw materials would change the distribution and size of asteroids over time. Spectroscopic observations might reveal unusual compositions in asteroid belts, perhaps unusually low concentrations of useful metals if those metals have been extensively mined. Debris from mining operations might create distinctive dust clouds with unusual properties. Stellar engineering represents the extreme end of technological signatures. Some theorists have proposed that advanced civilizations might manipulate stars themselves, extracting material from stars, changing stellar composition, or even moving stars through space using enormous thrusters. These Shkadov thrusters, named after physicist Leonid Shkadov, would use mirrors or other structures to create thrust from a star's own radiation pressure, allowing the star to be slowly moved over millions of years. A civilization might move their star to escape dangers like nearby supernovae, to position their star system optimally in the galaxy, or to transport their entire solar system on an interstellar journey. A moving star whose motion couldn't be explained by gravitational interactions with other objects might indicate such stellar engineering. Time also factors into detectability. A civilization's technological signatures change as technology evolves. Humanity's radio era might be brief, perhaps only a few centuries between when we developed radio technology and when we transitioned to communication methods that don't leak into space, like fiber optics or directed transmissions. An alien civilization might have a similarly brief radio-loud period. This means that civilizations at different technological stages would produce different signatures. An early industrial civilization might produce atmospheric pollution, but no radio signals. A spacefaring civilization might have extensive orbital infrastructure, but might no longer use radio for communication. An extremely advanced civilization might produce signatures we cannot yet imagine, using technologies and engineering approaches completely beyond our current conceptual framework. The absence of detected technosignatures, despite decades of searching, has led to discussions of the Fermi paradox. If technological civilizations are common, where are their signatures? Perhaps they're too rare or too distant. Perhaps they exist but avoid broadcasting or producing detectable signatures intentionally. Perhaps our detection methods are inadequate or focused on the wrong signatures. Or perhaps advanced civilizations develop technologies that produce no detectable signatures, or signatures we wouldn't recognize because we're not looking for them. What intelligent alien technology might reveal encompasses everything from deliberate messages transmitted across space to the inevitable waste heat and pollution from industrial processes, from the dimming of stars caused by megastructures to the reflected light from orbital infrastructure, from laser flashes used for communication to the gravitational anomalies created by stellar engineering. Each technological signature represents a different window into how civilizations develop, what they value, what problems they solve, and how they reshape their environments. Detecting any of these signatures would answer one of humanity's deepest questions: are we alone? And would provide our first glimpse into how other intelligences have developed technology, overcome challenges, and left their mark on the cosmos, transforming our understanding of what's possible, and revealing that the universe contains not just stars, planets, and lifeless matter, but minds that contemplate the cosmos just as we do, minds that build and create and reach toward the stars.